Section 12.1, Proportions and Similar Triangles. A proportion is a statement of the equality of two ratios. So that's the official definition. By ratios, we typically are going to mean fractions in that spot. So you could also say a proportion is a statement that two fractions are equal to one another. And when we work with a proportion of the form a over b equals c over d, if we know the value of 3 of the 4 variables, then we can always solve for the fourth variable. So we're going to look at a few applications where we're trying to solve for a quantity and we can set it up as a proportion, and we'll know 3 of the 4 pieces, so that will allow us to solve for the missing one. And I just want to show you some strategies to hopefully help that go smoothly. So let's look at an example. If 2 out of 7 students at a college are business majors, then what is the enrollment at the college if it has 4,172 business majors? So it looks like there's two types of things they're talking about here. We have business majors, just a portion of the student, and then they're talking about the enrollment. So by that, I would assume that they mean total enrollment. So that's all the students, including the business majors. So we have kind of overall students, and then we have a certain type, which would be the business majors. So when you go to set up your proportion, this ratio of two fractions, one of the key things to make this go smoothly is to think about which of those two variables is the unknown that we're trying to find, and that's total enrollment. So when you set up your fractions, you want the unknown to be on the top. So I'm going to make my fractions total enrollment for the numerator, and then business students for the denominator. And if I do that, then the thing they're asking me to find, the total enrollment, I can make that a variable and say that's x. And then I'm going to put that over the number of business majors at the school, which is 4,172. And there's one of my fractions. And I've already got the unknown in there. So now I want to set up another fraction that has no unknowns, but just numbers that are given. And we get that from right here. 2 out of 7 students at the college are business majors. So there's a temptation when I read that 2 out of 7 to write 2 over 7. But I have to make sure I'm consistent with this order that I've decided to write my unknowns or my information. Total enrollment on top, business students on the bottom. And it says 2 out of 7 are business majors. So the 2 is the business majors. And 2 out of every 7, that's out of every 7 students, business and otherwise combined. So I want to set it up like that. And once I do that, then I can try and solve for x. So if you think about this, we should be able to solve for x in one step because x is connected with only one other number, 4172. So if we think about how it's connected, we can just do the opposite of that connection to solve for x. So what I'm going to argue here is that the connection is division, so we should be able to get rid of it by multiplication. Let me write a new copy of this over here. So we have x over 4172 equals 7 over 2. And then I'm going to say because that 4172 is being divided into x, if I multiply by 4,172, those would cancel off. But what I do on the left side of the equation, I also have to do on the right-hand side so that things are balanced. This is over 1, if you want to think of that as a fraction, so I'll do that on both sides. These cancel, and I just have x over 1. So if all that's left is x over 1, then really all that's left is x. And on the other side, we just have some work to do with fractions. And we could think about that as cancellation. We could do long division. But we can also just go ahead and enter that into our calculator and see how it turns out. So I'm going to go for the calculator option on this one. Let me just go ahead and finish writing it again so that x is by itself. We have x equals 7 over 2 times 4,172 over 1. So I can just punch that into the calculator. Bring that in. We have 7 over 2 times 4172 over 1. You could skip the over 1 part if you want. And we get 14,602. So x is equal to 14,602, and I've solved for the variable. That's the good news. The bad news is when you read this problem, there was no x, so I shouldn't just give my answer as x equals. I should put that into words. So 14,602 is the total enrollment at the college. All right, so I would argue there's two real key steps in solving these problems with proportions. One of them is to make a decision about what's going to go where, and you should do that by trying to make sure that your unknown is on the top and then be consistent with that. So that's one key step. Decide what goes where, set it up consistently between the two fractions. And then the next one is just thinking about how do we get x by itself, and that's just like always in algebra, think about what's connected and what would be the opposite action. So if there's a division connecting those numbers, do a multiplication to cancel that out. So let's see how that works on another one. If 0.75 inches on a map represents 3 miles, then how many inches on the map represent 10 miles? So we have two different types of measurements here. We have inches on the map, and then we have miles, which would be like, in real life, on the planet, on Earth, however you want to think about that. So the thing that they're asking us to find, how many, that's inches on the map. So if I go by the same philosophy I did on the previous problem, then I'm going to put on the map up top, and because that's my unknown, this process works better if the unknown is on the top, and then I'll put in reality on the bottom. In reality, again, meaning on Earth or on the planet, something like that. All right, so how many inches on the map? We don't know, so I'll put an X for that. Equals 10 miles, so I'll put those 10 miles down on the bottom. And then when I set up the other fraction, I want to use this information that they gave me right here, and I just want to make sure I do that consistently. So this was the inches on the map. Maybe it would have been good to think about that too. Those were the inches, these were miles. So I'll go ahead and get those set up, and let's see, it was 0.75 inches over 3 miles. Just make sure that it's consistent. This was 10 miles, that was 3 miles, this was inches, this is inches. Once you get that set up, it should be pretty quick and easy to solve. You want to get that x by itself. There's a 10 connected to it by division. So if I multiply on the left by 10 over 1, those will cancel. Multiply by 10 over 1 on the right to keep things balanced. And then again, some of these you could do by hand, like 3 goes into 0.75, 0.25 times, and then times 10, that should be 2.5, I think, if I'm doing the math right in my head. But you're also welcome to use the calculator on these, so I'm just going to bring that in here and use the calculator. So we have 0.75 over 3, let me slide this over a little bit, times 10 over 1. And we get 2.5, which is what I got in my head also. Some of these you could do in your head, go for it. Some of them are kind of messier, and you can bring in the calculator. Either way is fine with me on these. So we got x equals 2.5, and then we just want to think about what they were asking and what that represented. That was inches on the map, so we would say 2.5 inches on the map. And that's good enough for me. If you wanted to make a full sentence, 2.5 inches on the map represents 10 miles. You could say a little bit more. All right, so the key reminder here is that when you're setting up a proportion, it's extremely important that you be consistent with the units used in the numerators and in the denominators, meaning that if you put the miles in the bottom here, you have to put the miles in the bottom there. If you decided inches on top on the first fraction, it has to be inches on top on the second one. Because of that, I think it's good to do these little reminders on the side about how you're choosing to do that. You might think it through for the first one and then get mixed up on the second one and just do it in the order it was written. This time the order it was written, this over that, is how we ended up doing it. But on the first one, the order it was written, 2 out of 7, is opposite of what I did. So it's not the order that those are written that's important. It's the units and being consistent with it and thinking about what number represents what, and again, just being very consistent with that on the top and the bottom. It actually doesn't officially matter if you get it upside down as long as you consistently got it upside down. But it is a harder problem to solve if the x is not on the top. Then it's a multi-step algebra process instead of just a single step. So I would definitely recommend that you're always trying to put your variable in the top or in the numerator. Things will just go a little bit smoother. All right, let's look at a couple more examples where we can solve using proportions. A family spends $475 on groceries in a 5-month period. Estimate the family's total money for groceries during a 3-month period. So again, I like to think about what the two variables are. One of them is about money, and the other one is about time. And the one that we're trying to estimate is the money. So since that's the one that's going to be our unknown, I want to put that money, which is going to be measured in dollars, on the top. And I'm going to want to put the period of time, which they're measuring in months, on the bottom. Just because I always want to have my unknown in the numerator, I usually will start off with the one about the question with the unknown. So estimate the family's total money. I don't know how much that is, so I'll put X. But that's during a 3-month period, so I'll put over 3. And then set that equal to another ratio where I'm being consistent with the units. So the family spends $475 in a 5-month period, so the amount of money for the top is $475. And the time period is 5 months for the bottom. And we want to get that x by itself, so it's connected by division. So if I multiply right here by 3 over 1, the 3's will cancel and x will be by itself. Do that on the other side for balance, and that'll tell me what x equals. And 5 does go into 475 evenly, and then so we could do that division and then multiply by 3. I think that would all be reasonable to do by hand, but a little bit time consuming. So I'm just going to jump in here with the calculator and figure out what my x is. The x is by itself, so I just need to work out this side over here. So at 475 over 5 times 3 over 1 is 285. So that's x, and then we want to think about what that represents. That was in the numerator, so that was money. And they asked us to estimate the total money for 3 months. So we estimate $285 in spending for a 3-month period. All right, so one of the things that we're counting on for doing this sort of math to work is that there's consistency here, that the family is basically spending about the same amount per month. Actually, if you look at this value right here, 475 over 5, that was $475 over 5 months. If you just divide that, we're saying they're spending $95 a month. If we multiply that by 3 months, that's where we're getting our 285. So you can kind of think it through a different way apart from the proportions. But do families always spend the exact same amount per month? Probably not. Is it usually about the same? It probably is, unless conditions change. So part B asks us about some possible changing conditions and how that would affect our answer. So assume that the kids in the family were home during the entire 3-month period, but were away for a large part of the 5-month period. Is the result you found in part A an underestimate or an overestimate? All right, so we'll just think this through. So maybe 5-month period, maybe that's the spring semester, and the 3 months is that they're coming home for summer, right? So we're trying to think how much money are we going to spend this summer? And we go, well, let's think about what we did over the last 5 months. But if the kids are coming home, is that really going to work? Probably not, right? So we weren't feeding the kids here. We are now. So we thought this would be just $285, but that was without the kids. If the kids are there, then we're going to end up needing to spend more, right? So with the kids home, we'll spend more. And so what does that imply? If we're going to spend more than 285, then 285 is an underestimate. right? So we did our planning, not thinking about the kids. So we think, oh, we're going to spend $285, but then they show up and they're eating all the cereal. All of a sudden, we are going to have underestimated how much we need to spend. Now, maybe I'm wrong about the kids. Maybe when the kids come home from school, they're so thankful for all we've done for them while they were away that they're going to take us out for food every night and we won't have to spend as much because the kids are treating. But then again, maybe they'll be eating all of our food. So this is what I think they expect us to be thinking about, that since the kids are home, there'll be more food that we need to be eating. So we'll have to spend more than we had estimated. All right, another place that we can use that we can use proportions is on work with similar triangles. So similar triangles are two triangles are called similar triangles if their corresponding angles are equal in measure. So that's the official kind of geometry definition of similar triangles. But another way of thinking about it is just to say that similar triangles have the same shape, but not necessarily the same size. So these two triangles look like they're similar because they appear to be similar in shape. Even though this one is bigger than that one, they still seem like the same shape, and that like maybe this is a shrunken down version of that one. That's what we kind of want to think of. And then from geometry, we have this statement here that the lengths of corresponding sides of two similar triangles are proportional. So let me explain what they mean by that while we solve this problem. So the given figures below show two similar triangles. So this kicks in and the corresponding sides are proportional. Find the length of the unknown side labeled with an X and then round to the second decimal place. All right, so we want to think about that same thing. Which one's going to be our numerator, which is going to be our denominator? So if this X is in this triangle, then I'm going to think of this as my numerator triangle, and this one as the denominator triangle. So when I set up my proportion, the first ratio I want to make sure I have the x in the numerator, so I'm going to put x over something. So what do I put it over? Well, they say corresponding sides are proportional. So what we're supposed to do is think about what side on this triangle corresponds to what side on this triangle. So this x corresponds to what over here. So just kind of looking at the shape, this x seems to correspond to the 4 meters. So because those are the corresponding sides, I would say x over 4. And then the way proportions work, we need another fraction to set that equal to. And they're saying just take another fraction where you're consistent with numerator and denominator and use sides that are corresponding to each other, and you'll get a proper setup. So the other numbers we know are 15 and 12. So we're going to make a fraction out of that. The question is 12 over 15 or 15 over 12. Because we put x in the numerator for the first fraction, we'll put 15 in the numerator for the second one, and then that corresponds to 12, so 15 over 12. So there's the setup, and then we just want to do the algebra steps to get x by itself. Multiply by 4 on the left, those cancel. Multiply by 4 on the right. There's some canceling we can do there. 4 goes into 12 3 times. I think, I've done so many on the calculator. Here goes one by hand. This one looks fairly simple. 4 goes into 12 3 times, and then that 3 goes into that 15 5 times. So it looks like it's going to be x equals 5. So we can feel a little proud there. We did one on our own, right, without the calculator, but I'll verify it with the calculator too. So before all the scribbling started, we had 15 over 12 times 4. And there's the same 5. So either way is okay. They're really telling us they don't mind us using the calculator right here when they talk about rounding to the second decimal place. So this one just happened to work out kind of easy, so I went ahead and did it by hand. I think on my math lab, if they tell you to round to the second decimal place, then even if you get a really nice number like 5, you should still write 5.00 so that you're following those directions. The units on this side length would be meters. I guess I could argue we don't have to write meters because it already says x meters, but I think even so, I would probably still do it just to emphasize what the units are. So that side length right there is 5 meters according to similar triangles. All right, let's try another one. So this time the x is on this triangle over here, so this will be our numerator and this one will be our denominator. So we're going to take that x over, And that's this longest side right here on the triangle. So here's the longest side on this one. So x over 10, seems like we're doing corresponding. And then we have the 7 and the 4 are also corresponding. This side seems to match up with that side. And then just pay attention to the numerator denominator. So we'll do 7 over 4 rather than 4 over 7. So there's the setup according to the similar triangles. And then we just need to do the algebra, multiply by 10 to cancel here, multiply by 10 on the other side as well. And we could do some work by hand here, but we are going to end up with a decimal. So I'll just go ahead and bring the calculator in on this one. So 7 divided by 4 times 10 is 17.5. So it looks like x equals 17.5. I would write 0.50 just because they told us up here to use 2 decimals, so make sure we're following that. And then this time our measurements were in inches. I would also just kind of check to see, does that make sense? So this was 4 to 7, so this triangle has bigger measurements. So if this one's 10, we expect something a little bigger over here, so 17.5 makes sense. When you go from this 4 to 7, if you doubled 4, that would be 8. This is a little smaller than the double. If you doubled 10, you'd get 20, and we came up with something a little smaller than 20. So I think it's good to kind of think about, does it match up visually with what you're calculating on the math too, because you might catch some mistakes that way. So similar triangles, fairly common use of proportions, so that's how that one works. Alright, just a quick little bit of bonus material here. Why is it that we would use similar triangles? What's an occasion we might use it for? So let's say we had level ground and we had a tree growing there. This is about the only kind of tree I can draw, so I guess it's a pine tree that we're looking at. And we want to know how tall that is. That's going to be pretty difficult to measure, most pine trees being pretty tall, right? But let's say that I was standing nearby. I wish I was that thin, I guess. I don't know, maybe not. That's a little too thin. But there I am, admiring the tree. So how could I figure out how tall the tree is? Well, let's imagine that we have the sun right here. Don't imagine that too literally as right there, because if the sun is that close to the tree, we're all dead, right? So the sun's way out there, but somewhere up in the sky, and its rays are coming in, and the tree blocks them, so it creates a shadow on the ground. Now, because the sun is so far away, the ray of the sun will come in at the exact same angle when it comes across my head, and then it'll form a shadow right here. And the triangle here and the triangle there will be similar triangles because the rays of the sun are coming in at the same angle. Alright, so we've got a similar triangle here formed by like the ray of the sun, the shadow, and the tree, with me, my shadow, and the rays of the sun. So what are we trying to figure out? That's how tall the tree is. So we could say, let's maybe put an H there for the height. And let's say that we measured this shadow and it was 40 feet long. Well, I know how tall I am. I'm 6 feet tall. And then we could measure my shadow, and let's say my shadow was 3.7 feet long. Then I could use similar triangles to try and figure out how tall the tree is. I would just set up this triangle as the numerator because it has the unknown in it. And then this would become my denominator triangle. And I would do H over 6 equals, so I did big triangle over corresponding on the small triangle. So then this is my numerator, so I would do 40 over 3.7. And then I could multiply both sides by 6. That gets H by itself. Bring the calculator in. 40 divided by 3.7 times 6. Get a messy number there because I was just making up numbers on the fly. But it looks like H is approximately 64.86. We'll go with the rounding they asked us for on the previous page. And then I said I was 6 feet tall, so everything here I was measuring in feet, 40 feet, 3.7 feet, so this would also be feet. So then based on similar triangles, the tree is 64.86 feet tall. Now if it really was that tall, it'd be hard to climb up there and measure it, but it wouldn't be hard to measure its shadow because that's at ground level. So this is one technique that we could use to measure the tree, and it's kind of a nice little use of similar triangles. So there, it's not just abstract, there's some use in the real world for it right there. Okay, hope that little bonus material was helpful.